For Lesson 22, we're going to look at writing and evaluating expressions that include exponents. So in class, there is a folding paper activity, and you may be able to do this at home or where you're at, but you would want to take the paper, fold it in half, and see how many times you think you can fold it in half until it just won't fold any longer. You need to make a prediction on how many times you think that will happen. And then we're going to make a table based on that activity. Before any folding, there is only one layer of paper. Now notice our three columns: the number of folds, the number of paper layers that result, the layers of paper, and the number of paper layers written as a power of 2. Because every time we fold the paper, it is folding in half, which is 2 parts. So when we start with 0 folds, we have one layer of paper. This is really extremely important. With 0 folds, we do not have 0 paper layers because we would not have any paper if that were the case. So we have one layer of paper because we have one sheet of paper. The paper layers written as a power of 2 are 2 to the 0 power because we haven't folded it yet. But 2 to the 0 power is 1 because we have one paper to start with. Now, when we fold it one time, we will have 2 layers of paper, and that is 2 to the first power. We've folded it once. When we fold it twice, we will have 4 layers of paper, which is 2 to the second power. 2 times 2 is 4. When we fold it 3 times, we will have 8 layers of paper, and that is 2 to the third power. Folded 4 times, we will have 16 layers. I wonder if you've been able to get this far. And that is 2 to the fourth power. Folded 5 times, we'll have 32. That is 2 to the fifth power. Six times, we have 64, which is 2 to the sixth power. Notice we're doubling every time. If you were able to fold it 7 times, wow, it's 128, which is 2 to the seventh power. And finally, if you made it to 8 times, it's 256 layers. I don't think anybody got that far, and that's 2 to the 8th power. Now, are you able to continue folding the paper indefinitely? No, because the paper gets too small and thick in order to fold anymore. How could you use a calculator to find the next number in this series? Well, you would multiply by 2 each time. So the relationship between the number of folds and the number of layers, as the number of folds increases by 1, the number of layers doubles. Of course, that is multiplying by 2. And it's represented in the exponential form I could use 2 as a base and the number of folds as the exponent. So if you fold a paper F times, space here. If you fold a number F times, there would be 2 to the F power layers. If the paper were to be cut instead of folded, the height of the stack would double at each successive stage, and it would be possible to continue because we would not have all of that thickness involved as well. So write an expression that describes how many layers of paper result from 16 cuts. That would be 2 to the 16th power. And if we evaluate that using a calculator, naturally, that would be 65,536 layers. Exponential relationships are very common in things in medicine, for example. So we're going to take a look at bacterial infections. Bacteria are microscopic one-celled organisms that reproduce in a couple of different ways, but one of which is called a binary fission. In binary fission, a bacterium increases its size until it's large enough to split into 2 parts that are identical. And these 2 grow until they are both large enough to split into 2 individual bacteria again. This continues as long as the growing conditions are favorable, meaning that it hasn't been treated or killed by some medication that's added to the system. So as we see in the diagram, it starts with 1 bacteria. Okay, so we actually have not shown the 0 level before it has split. But if we were to show the 0 level, remember in our last table, let's scroll up here, before there were any folds at the 0 level, 2 to the 0 power was 1 paper layer, because we had to start with 1 piece of paper. So the bacterial infection is the same way. We would start with 1 bacteria. It will not, on the 0 level, it would not have split yet. So it would be 2 to the 0 power, which is 1 bacteria. Our table then starts at generation 1. And generation 1 is when the initial bacteria splits for the first time. 2 to the first power, which is 2. Then, in our second level, we have these 2 bacteria. Now remember, these bacteria are not reproducing an additional bacteria, but they are actually growing and splitting themselves. So on the next level, these 2 are this bacteria that split itself. So on that level, then, we have 4. This is the second split. We have 4 bacteria. At the third split, it's this level right here. Remember 0, 1, 2, 3. This is our third split. There are 8 bacteria, or 2 to the third power. So on the fourth split, we're going to have 16 bacteria, and that is 2 to the fourth power. On the fifth split, we're going to have 32 bacteria, which is 2 to the fifth power. On the sixth split, we'll have 64, which is 2 to the 6th power, seventh split will have 128, which is 2 to the 7th power. Eighth will have 256, which is 2 to the 8th power. And the ninth will have 512, which is 2 to the 9th power. 1024, 2 to the 10th power. 2048, 4096, 8192, and 16,384. So as you see, the longer the bacteria has in a hospitable environment, the worse or the sicker the individual will be. How many generations would it take until there were over 1 million bacteria present? Well, we would need to continue, but we would find 20 generations, 2 to the 20th power, will equal 1,048,576. Under the right growing conditions, many bacteria can reproduce every 15 minutes. Under these conditions, how long would it take for one bacterium to reproduce itself into more than 1 million bacterium? So what we're looking then is it needs to reproduce 20 times. So we would have 20 times 15, which equals 300 minutes or 5 hours. That needs an exclamation mark. 5 hours under the right growing conditions for a bacterium 1 to turn into over 1 million. So we're going to write an expression for how many bacteria would be present after G generations. And again, our base is 2 because it is splitting each time. And our exponent would be G. Let's change gears here to example 3. We're looking at the volume of a rectangular solid. Now this box has a width of W, width. The height of the box is twice the width, 2 times W, and the length of the box is 3 times the width. That is, the width, height, and length of a rectangular prism are in the ratio of 1, 2, 3. 1, 2, 3. For rectangular solids like this, the volume is calculated by multiplying length times width times height. Remember, it's all multiplication. So multiplication is commutative. You can multiply them in any order. The volume of this particular rectangular solid would be 3W times 2W. And then, because it is all multiplication, we can change the order and put all of our numbers together, 3 times 2, and all of our variables together, w times w times w, which will give us 6 w to the third power, because when we repeat multiply, that is an exponential relationship. So following the example above, we're going to calculate the volume of these rectangular solids given the width. So we're going to be given one measurement, and then we're going to calculate the volume from those given measurements. So if our width is 1, our volume would be 6 times 1 to the third power. And 1 to the third power is 1 times 1 times 1, which is 1. And 6 times 1 is 6. So our volume in centimeters cubed is 6 centimeters cubed. Now, if the width is 2, now we have 6 times 2 to the third power. And that is actually 6 times 8, because 2 to the third power is 8. So now we have 48 cubic centimeters. If the width is 3, we would have 3 to the third power. And 3 to the third power is 27. So now we're multiplying 6 times 27, which is 162 cubic centimeters. If our width is 4, it'll be 6 times 4 cubed, which is 64. 6 times 64 is 384 cubic centimeters. And so it follows that 6 times w cubed and our units are in cubic centimeters would be the formula. Please notice that I did not put w in parentheses in this case. I used parentheses in the other cases because I knew that I had to multiply. In this case, I know that I have to multiply because it is a variable, but the 3, the exponent of the 3, applies only to the number directly in front of it. It does not apply to the 6. So this is the correct way to write it. Your problem set will have more practice on different scenarios.